we're going to finish up by looking at section 3.2. And 3.2 really has three distinct ideas in it. The idea of continuity, intermediate value, and end behavior. I've already given you kind of some ideas about what each of those mean. Maybe the intermediate value I haven't touched on as much, but continuity and end behavior, I have kind of mentioned those. I just never called them that. So most graphing calculators, or I should say some, I won't even say most, depends. But some graphing calculators assume that what you want to draw should always be connected. For example, if I were to do something like this, 3 divided by x minus 2, what value can I not use for x? 2. So there's a problem at 2 in this graph. And if I do zoom 6, you're going to see it get pretty weird as x gets close to 2. There's a break in the graph. So you could not draw this without lifting your pencil. You would have to draw one piece, lift, put it back down, and draw the second piece, because there's a break in the domain. Older calculators would take this graph, which is drawn correctly, that is how it should look, and they would draw it like this. We would try to connect it. It should not be connected. There is no connection between those two graphs, those two parts. So newer calculators can account for the fact, you'll watch, it draws it a little bit slower, but it's thinking about it a little bit more, and it knows that those two pieces shouldn't be connected. This idea of whether a graph is connected or not connected has to do with what's called continuity. I'm not going to do 1 over x minus 3. I just did 1 over x minus 2. It's the same idea. When you draw any of these graphs, what you want to do is ask yourself, can you trace the graph without lifting the pencil? That's the idea. This is an integer function I think we looked at. It looked like a set of steps.
How do you get to integer?
It's under math, number,
It's number 5.
and 5. Did we look at that graph before?
Yes.
Can you trace that without lifting your pencil?
No.
No, you have to lift it infinitely many times. Because at every step you got to lift, put it back down on the next step. Now, how about something like h of x? This is a parabola. Could you draw that without lifting your pencil?
Yes.
Yes. So this one was a no. This one was a no. This one was a yes. So what does that mean? It means that this parabola is a continuous function. You can trace it without lifting your pencil. And I know it's not super mathematical to say it, but that's the most common sense way to think about it to make it easy. So we say that a function is continuous over a certain interval if basically you could start anywhere and stop anywhere in that interval and trace the graph without lifting your pencil. So sometimes we're not saying, is the entire graph continuous? We might just say, is a certain section continuous? And a lot of times, yes, you can find a small section on any graph that is continuous if you make it small enough. So if I had an interval from like 0 to 10, and I said to you that my graph was continuous over the interval from 0 to 10, that means I could put my pencil on 0, and I could trace all the way to 10, and never lift my pencil when I do it.
So it is continuous if you don't have to lift your pencil?
Yes, once you lift your pencil, that's discontinuous. That means you have some kind of break in your graph, usually caused by a problem in the domain. That could be a divide by 0, like I showed you. If you can't do that, then your graph is discontinuous. Some graphs don't have discontinuities, like a parabola. You could start anywhere on a parabola, you could stop anywhere, and no matter where you start and stop, you will never have to lift your pencil. Parabolas do not have any discontinuities in the graph. The step function, yes, that one does.
Right, so parabolas are always continuous.
Yes, parabolas cannot be discontinuous. They are always continuous. In fact, every single polynomial is continuous.
Are most things that we see with the IUT, are those always going to be discontinuous?
That's a step function, yes.
Okay, alright.
So step functions are always discontinuous. Yeah.
Okay, cool.
So it's possible to look at a graph and find some sections that are continuous and some sections that are discontinuous if you have the right picture. So we're going to look at the graph of 1 over x. Now, what number are you not allowed to use for x there? 0. So it's going to do something weird at 0, kind of like it did before. It's going to break itself into 2 pieces. It's technically a hyperbola. We'll talk about those when we do conics. Also, the graph is a little misleading because
It looks like it stops.
it doesn't stop at 1, 2, 3, 4, 5, 6.5. It doesn't stop there. It's just once the calculator starts trying to draw something that gets too steep, it can't do it. Just the limitation of the calculator. Because if I were to plug in like 0.001 for x, 1 divided by 0.001 is 1,000. So when I'm at 0.001, my graph is up at 1,000. It's very steep. So what I want to do is look at this graph and find 2 intervals that are continuous and 2 intervals that are discontinuous. So what I'm looking for you to name is a starting point and a stopping point that I could trace from without lifting my pencil first. Could someone give me a starting x value and an ending x value? Yeah.
Negative infinity, or
Yeah, I guess we could do negative infinity.
and then to like an open 0.
Whew. Just barely. I think technically that is continuous. Because it's obviously unbounded, but you would never have to lift your pencil, assuming you could draw to negative infinity. You'd never have to lift your pencil to do it. Can someone give me another interval?
Alright, so the best.
Yeah?
Open on 0 to infinity.
Okay, so that's kind of like that one. How about a bounded interval? I'm looking for something simple. Yeah.
Yeah, like closed -9 to -5.
Perfect. Yeah. So open, closed, that doesn't really matter in this case. But you could trace from -9 to -5. Like that. I just did. All right.
I see.
So that's considered a continuous interval. I think this one would be considered continuous too, because you'd never lift your pencil. But you'd have to draw forever to do it. How about discontinuous? Could somebody give me an interval where I would have to lift my pencil if you told me the start and the stop? Yeah?
-1.
Yes. Whether it's open, closed, that doesn't really matter. But yes, any interval that passes through the number 0 in this problem is discontinuous. Because 0 is a problem. You have to lift and put it back. Any questions on that? All right. There are 3 main ways that a function can have a discontinuity in it. One way is the way that I've shown you a couple times already, is that you would end up dividing by 0. That's called an undefined value in the function. A value that would cause you to divide by 0. Another thing that can happen is you can have breaks in the function. Breaks are not undefined values. The domain for the integer function is all real numbers. You can plug in anything you want. The issue is this function causes rounding to happen. So when you round it, it rounds to the nearest integer, which means there's nothing between, say, 3 and 4. It jumps all of a sudden. So this jump is called a break. But it's a different reason for a discontinuity than an undefined value. Okay, undefined is like you did something you're not allowed to do in math, like divide by 0. Those two are pretty easy to see. Okay, I've shown you both of those graphs. The third one is not easy to see. It's a hole in the graph.
Oh.
And the hole is infinitely small. So I don't care if you keep zooming in. You're never going to see it. The only way you know it's there is if you look at the problem you were given and figure it out that way. You cannot figure out your graph has a hole by looking at a picture. Here's an example. Let's graph that. A hole is a special type of undefined value. It's not detectable on a graph. Okay. It's still undefined like the first one, but it's not detectable on a graph. So that's the important thing. So let's type in x squared plus 3x plus 2 divided by x plus 2. What value are you not allowed to use for x here? Negative 2. Let's hit graph and watch what happens. Didn't skip a beat, just kept drawing. Did the graph show anything weird happening at negative 2? No. Negative 2 is right here. Right there. Negative 2. So, negative 2, there is something weird happening. The way you can tell is if you set your table up, I think we've done this so that you can type values into it. Try putting negative 2 into that formula. Negative 2. Error. Can't do it. You can do negative 1.999. That's fine. You could do negative 2.00001, but you can't do negative 2. And the reason is, look at your numerator.
How'd you get to the table again?
Second, and then graph. That numerator is factorable. How does it factor? X plus 1, x plus 2. That's the problem. You factored it and you have a common factor in the top and in the bottom. So when you graph this, essentially it's going to look just like the graph of y equals x plus 1. Watch this. Basically looks like exactly the same graph, except we know that we had a hole because we had a common factor in the top and in the bottom. That's what causes a hole. When you have a common factor, you could cancel out. So let's change it so we don't have a common factor. Let's just change it from plus 2 to plus 3. Well, now the top doesn't factor as x plus 1, x plus 2, and it's going to look completely different. Now, we have an undefined value, and it's very easy to see that it's undefined. This more falls into like case 1. This is like a special type of case 1. Okay? So any questions on that?
Wait, alright, so what did you plug into the third graph?
I just plugged in +3. Yeah.
Alright, is the only way to find if there is a hole to try and solve it algebraically and see if you have two of the same?
So the only way to tell algebraically is to factor your numerator and see if it has this common factor with the denominator. If there's a common factor, then yes, you have a hole. You could end up with multiple holes if you had multiple factors that were the same. And the way you should technically draw it, when you know there's a hole in there, you should not draw it so it looks like a solid line. You should exaggerate it so we can see it clearly. That's how you draw a graph with a hole. Make an open circle right in the middle of it, or wherever the hole is. So, I think I already said this to you, but the domain of polynomials is all real numbers. There are no undefined values in polynomials. You never would divide by 0. You would never take the square root of a negative. That means you can draw polynomials, the entire thing, without ever lifting your pencil. That's called a continuous function. Continuous function doesn't just mean that there's a small section you could draw without lifting your pencil. It means the whole thing can be drawn without ever lifting your pencil. In fact, in a polynomial, it is impossible to find a section that is discontinuous. There isn't one. It's continuous everywhere. Just think of a parabola. Any questions on that idea?
Alright, so doesn't that just say that every polynomial is continuous?
Yeah, every polynomial is continuous. Parabolas, cubics, all of them. Polynomials are generally easier functions to work with than some of the other ones we're going to study because of that. You don't have to worry about undefined values or breaks or holes. It doesn't happen. Right. So that's the idea of continuity. Okay, second idea, intermediate value. It's a pretty common sense idea. I just haven't really explained it to you yet. But the idea of intermediate value is tied into continuity. Here's an example. Let's say that you had water in a pan at room temperature. You put it on the stove and you start boiling. If it started out at, say, 70 degrees, and when it's boiling, it's 212, what temperatures is it going to go through in between 70 and 212? All of them. So it'll go through 80 at some point. How about 90.4? 107.264. Yeah. It's gonna go through every single possible number that exists between where it started and where it stops. Boiling water would be considered like a continuous process. You don't skip anything as you go from the start to the end. Counting is not a continuous process. If I count how many people are in here, 1, 2, 3, 4, 5, I'm skipping a bunch of numbers. I didn't use 1.6, I didn't use 2.417, I didn't use any of those. So the idea of an intermediate value is that if you have something continuous, and you know where you start, and you know where you stop, you'll go through every value in between. That's the intermediate value property. Explained simply. So now let me give you kind of a more mathematical way to explain it. If you have a function that is continuous on an interval between a starting value and a stopping value, then you will go through every single y value between f of your starting value and f of your stopping value. I can sketch that up. So there's a graph. Let's say I look at the interval, that's A, and over here is B. That is continuous because I never have to lift my pencil to trace from A to B. So what I'm saying is that if I make up numbers, let's say that A has a y value of 0, because it looks like A is right on the x-axis. And let's say B had a y value of, I don't know, 4. I'm starting at a y value of 0. I'm ending, roughly, at a y value of 4. The intermediate value theorem states that I will pass through every single y value between 0 and 4. I might pass through more, but at a minimum, I'm going to pass through every value from 0 to 4. Now, in this case, A does dip down lower. Well, I can't guarantee you're going to go lower than 0. I don't know that. But I guarantee if you're going to travel from A to B, there's no way to get there, no matter what you try to do, without going through every single value between 0 and 4 at some point, maybe even more than once. That's called the intermediate value theorem. Any question on that idea? Another application of that is if you have a continuous function, and it goes up forever and it goes down forever, what value are you guaranteed to go through at some point? If the graph goes up forever and down forever. 0. That's a very important concept. Okay? If you travel a continuous function and it goes up and down forever, you will cross the x-axis at some point. You have to. There's no way to go from negative infinity to positive infinity without going through 0. In fact, without going through every single number in between at some point. Okay, so let's try this. Here's our function. F of x equals 3x minus 4. And I want to find a value that I can plug in to my formula and get a result of 15. First, I want to see if that's even doable. Okay, I'm sure most people could just change this to 15 and solve it. But what I'm interested in is this process of thinking behind it. We're going from negative 10 to positive 10 on the x-axis. And we're drawing a line with a slope of 3 and a y-intercept of negative 4. First of all, if you draw a line, is that a continuous function?
Yes.
Okay, so it already meets the criteria that it has to meet to use this idea. Step functions would not apply to this at all. They're not continuous. But the line is continuous. Okay, good. Now, let's find the y value if we plug in negative 10. What's 3 times negative 10 minus 4? Okay, so we are starting at negative 34 in this interval. I know a line goes down forever, but we're looking in this interval. We're starting at negative 34, and we're going to go up to what's the highest value that we reach? 26 in this interval. So we are traveling from negative 34 up to 26 on the y-axis without ever lifting our pencil because we're drawing a straight line. Am I going to go through 15 at some point?
Yes.
Absolutely. Am I going to go through 70?
17?
70.
No.
No, I'm not going to go through 70 between negative 10 and 10. So that wouldn't work. But 15 works. Where do I hit 15? What number would you plug in for x so that you get 15 for y. That's the algebra part. Now we just solve it. 3x minus 4. So x equals 19 thirds.
Thanks.
So the point was just to figure out an x value between negative 10 and 10 where I would hit 15. But the first thing I did was check to see if that was even doable based off the intermediate value theorem. 15 is an intermediate value between negative 34 and 26. So I know it would work. And then I found what made it work.
So the 19 thirds is the final answer.
Yep. Any question on that thinking? Okay, let's do that one. Let's look at this one. So it says, let your function equal x to the fifth plus 2x minus 1. Okay, I'll type that in. X to the fifth plus 2x minus 1. And I'm going to go to the table. It says prove that there is a 0 in the interval between 0.25 and 0.75. Another way of saying that is prove to me that this graph would cross the x-axis somewhere between those two numbers. How could I prove that? I actually already hinted at a little bit how I would do it. Yeah?
Put 0 in for x on the table.
Well, 0 is outside of our interval. So we do want to plug in something and see where it's at, and then something else and see where that's at. But I don't know if this is going to cross at 0. That would be outside the scope of this question.
Do we not plug in 0.25 for x like we did?
No, we do.
Okay.
Plug in 0.25 and see where you're at. Okay, 0.25 gives me a y value of negative 4.99. Wait, what was it? Negative 0.499, sorry. Okay. What else do you think I'd have to do?
Wait, how'd you do that so fast?
I just use the table
Oh, okay.
on the calculator. If you don't have a table, you can do it out, but the table's fast. Yeah, what do I do next? Plug in 0.75. Okay. 0.737. Okay, now what? Well, that's all you have to explain, why you know it works. Just prove to me why you know it works. You don't actually have to find where it crosses.
Because you have a negative number, which is always below 0, and you also have a positive number, so in between them, drawing a continuous line, it has to hit 0.
Right, the key, I was hoping you would have said the word continuous, because that's important. So, the way I would write this down is, so you start at a y value that is negative. So you start at a y value that's negative and end at a positive. The function that we're using is continuous. If it wasn't continuous, this wouldn't work. But the function we're using is a 5th degree polynomial. That is continuous. So the function is continuous, which means to go from a negative value to a positive value, to go from negative to positive, you have to pass through 0. There's no way to skip it. So to go from a negative to a positive, you must go through 0. You start at a y value that's negative, you end at a positive. The function is continuous, which means as you go from a negative to a positive, you will go through every value in between those two numbers. Yeah.
So I'm guessing that's what we're supposed to do on the problems and not, because what I see just the difference is if you just put y as 0 and then you do an x value in between those two.
Yeah, so in this one, they don't want you to solve.
Okay,
They just want you to-
This is 0 in the interval, so if you put y as 0 and you get an x value in between those, is that not also prove it?
So that would be a way you could prove it algebraically if you know how to solve a fifth degree polynomial.
Okay.
I don't know, because we could, using a graphing calculator as a proof, can't really do that.
Oh.
But if you could put a 0 in here and solve that algebraically, absolutely, that would prove it as well. But even, I have no idea how you solve that without. Quadratic I would know how to do, but not that. So that's all they were looking for. Any question on that? Okay. So that was the second thing, intermediate value. The third thing, I think it's a little easier to grasp. It's more concrete, less theoretical. And it has to do with end behavior. End behavior describes what a continuous function looks like on the ends of it. So if you drew something like that, and I wanted to describe the end behavior, I would say that it goes down on the left, it goes up on the right. One way to describe the end behavior is like this. Down on the left, up on the right, in that particular graph. There's really 4 possible end behaviors. Down, up, down, up, and down, down. So end behavior doesn't care about what's happening in the middle. Who cares? End behavior is looking at, all right, big picture. What's the right side doing? What's the left side doing? And polynomials always have one of those 4 end behaviors. Up, down, 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 up. So I'm going to show you 2 ways that you can write end behavior. One is a way that's more calculus kind of notation, and one is a way that uses more of like arrows. But the graph y equals x cubed looks like this. The way you describe the end behavior of that, if you use arrows, is what's happening to your y value on the left. That goes here. It's going down. What happens to the y value on the right? It's going up. This notation, let me read it exactly the way it's written, and then I'll read it simplifying it a little bit. This is pronounced the limit, that's what that stands for, the limit of f of x as x approaches infinity, and the limit of f of x as x approaches negative infinity. This basically means what is happening to y as x heads to the right. What is happening to y as x heads to the left. That's what that means. So let's look at this picture. What is happening to the y value as x heads to the right? Yeah?
Y approaches infinity.
The y value is going up forever, and in math, going up forever is called infinity. What's happening to the y value as x heads to the left?
That would just be negative infinity.
Negative infinity. Yep. So this part means this. That part means, did I do it backwards? Sorry. That's the red part, and that's the green part. The green part's going down, the red part's going up. That's green. So there are 4 different types of end behaviors. I already said this for polynomials. Up, up, think of a parabola. Goes up on each side. Flip it over, goes down on each side. And then something like the one we just did, one ends up, one ends down.
Wait, was there always a common between them like that? The other ones?
Yeah.
Okay, alright, I didn't see that.
Yeah. So let's look at this. Let's just do f of x equals x to the 4th. I'll graph it for you because I know quickly what it looks like. Kind of looks like parabola, but the bottom is a little flatter. But that's what y equals x to the 4th looks like.
Alright.
Good try. So what would be, let's write it this way. What's happening to y as x approaches infinity? As x heads to the right, y heads up forever. What's happening to y as x approaches negative infinity? It also approaches infinity. This is the type of end behavior that is up, up. Up on the left, up on the right. A little more basic way to say it, a little more formal way. Questions on that? So there's a way you can tell very quickly which one of the 4 end behaviors it is. And no matter how long of a polynomial you write, there are only 2 numbers there that matter for whether this is up, 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 down, or whatever. Anyone think they know what the 2 numbers are that are important? Yeah?
Highest exponent and that coefficient.
Yep. Those are the only 2 numbers that are going to make a difference in the end behavior. Everything else might cause little twists and turns, but it's not going to affect the end behavior. So the first case is where this number in front is a positive value. If it's a positive value, and your exponent is an even, like y equals x squared, that's an up, up. If it's a positive value, and your exponent is an odd, that's down. If the number in front is a negative, and your exponent is even, like y equals negative 2x to the 4th, that would be down, down on the end behavior. If the number in front is negative, and the exponent is an odd, negative 5x cubed, that would be up on the left, down on the right. So that chart summarizes end behavior for polynomials.
Is that the y equation? Are those just examples?
It's just examples of a negative coefficient with an even exponent and an odd. Doesn't matter what particular even or odd number. You just look if it's even or if it's odd.
So you can find it out without even practicing.
Yes. And the reason you can do that is because that first term in the polynomial is called the leading term. The leading term controls the end behavior. It controls the overall look of what's going to happen in that polynomial. All the other terms just cause twists and turns. That's it. And that leading term, it is called the leading term, but it has a special name. So if you write something like 8x to the fourth minus 5x squared plus 3x minus 2, this is your leading term. 8x to the fourth. What would the end behavior be of that? Up.
What do you mean by dominates polynomial?
It controls what the polynomial is going to look like.
Okay.
It's the most powerful factor term in the polynomial. Now, I call it the leading term, but what it's really called is the EBM. That leading term is called the end behavior model. So what that basically means is if I were to graph this whole thing in y1, and then I were to graph just the EBM in y2, and I zoom out far enough, they would basically look the same. Yeah, there's some close-up details that might be different with these other terms, but if you zoom way out to like the tens of thousands, the EBM and the original are going to look almost identical.
And EBM stands for end behavior model.
Stands for end behavior model. So the end behavior model is just the leading term. So if they ask you on a question, write down the EBM of the following. They just want to know the leading term. Well, we're going to finish up by doing a graph, and then we'll graph the EBM and see if they look the same. All these other terms don't make a difference. It's just extra. Okay, if all you want is the big picture of what it looks like, look at the leading term, and that alone will tell you what it looks like.
And then, so the n as a subscript below a, that's just used to look at like the n even, n odd, but it's only really situated like in the actual equation as an exponent of x.
Yeah, so it would just represent like if this was my fifth exponent with the fifth term, then my coefficient with the fourth term, then my coefficient with the third term.
Okay.
So it's just telling you the coefficient of what term you're looking at. The fifth term, the fourth term, the third term, and so on.
Okay, thank you.
Yep. All right, so let's finish up with this one. I want to graph both of those functions, this and this. What's this thing called again? The 2x cubed? The leading term.
Or the EBM.
But the EBM, yeah.
End behavior model.
So I want to graph the EBM of f of x, and I want to graph f of x itself. And let's start with the first window they give. So we've got 2x cubed minus 7x squared minus 8x plus 16. And then let's graph 2x cubed on y2. Let's set our window. Negative 8 to 8. What values are those? Well, the negative 8 and 8, where are those going?
Those are the y min and x y. Yeah, x min and x max.
Yeah, so x min and x max. And the negative 100 to 100. The y min and the y max. Now I told you that the EBM and the original should look the same if you zoom out enough. We didn't zoom out there on the x-axis at all. So let's see what this looks like. That's the original. And that's the graph of the EBM. Do they look the same?
No.
No. They didn't look the same, but you're zoomed in quite a bit. Let's zoom out. So let's go and look at this from even further away. Negative 100 to 100. No, sorry, negative 40 to 40. That would probably be even better, but let's do negative 40 to 40. And negative 10,000 to 10,000. Remember what they looked like before. They didn't look the same at all.
No way to let's freeze.
Once the second one graphs, I want you to tell me how close they look or if they don't look close.
Pretty close. You can definitely still tell they're the same. They're different.
Yeah, it's pretty close, but again, all these other terms are affecting are small details near the origin, not the overall picture of the graph.
Oh, I see. Interesting.
That's what I'm trying to show you. Okay, so 2x cubed is called the end behavior model. I think, actually, just tell me this real quick. What would be the EBM of that? Yeah, that's it. That's the EBM. Okay, so we've got about 5 minutes. I might have enough time to get all the topics for the test on the board while you're still here. If I don't, I will pause the video and make sure they are in the video for tonight. That's the homework. And the test topics, I will put right to the right of it.